the last thing I want to say, so Fergus is a PhD researcher working in computational imaging and simulation techniques in biomedicine, and at the Leeds Institute of Cardiovascular and Metabolic Medicine. So this will be from the health part across at University of Leeds. And his research interests are in the fields of physics-informed machine learning and super resolution in vivo cardiac flow data. Right, so that sets the scene. Great.
Right, and thanks for wanting to do this.
No, it's good. That's a good thing to do.
You just get going after that.
Okay. So I'm going to keep the talk kind of shortish. I think it'll run about half an hour instead of 45 minutes, because I think it's probably better to do this hands-on, really, in terms of actually learning how to use pins. So I thought I'd start with a little quote from the abstract of the original paper by Raisi and Karniadakis. So they say, we introduce physics-informed neural networks that are trained to solve supervised learning tasks while respecting any given law of physics described by general nonlinear partial differential equations. The resulting neural networks form a new class of data-efficient universal function approximators that naturally encode any underlying physical laws as prior information. So I thought that kind of encapsulates quite nicely what these things are about. So the first few slides are just going to be some examples from the initial sort of papers, just outlining kind of the broad kind of scenarios in which we can use these. So firstly, it's forward approximation of functions. So in this example here, they are looking at simulating the Schrödinger equation. So what we're using here is initial and boundary condition data. So these little black crosses on the t equals 0 line and across the x equals -5 and 5 lines represent the data that's used. So this is initial condition data and boundary condition data. And the pin is capable of predicting the solution across this entire spatio-temporal domain. So they're not only useful for forward inference, they're also capable of inversely discovering solution fields and also kind of parameters, unknown parameters within PDEs. So this example here doesn't use any boundary or initial condition data, but uses velocity data that's randomly distributed through the spatio-temporal domain. And it's capable of predicting this pressure field here up to a constant. As you can see, there's a really good qualitative agreement between the predicted pressure and the exact pressure here. And I think this is quite impressive because you don't use any pressure data whatsoever. And it's also capable of inferring these unknown parameters in the PDE as well. So say we don't know the density or the viscosity of the fluid, and we can inversely discover these. So taking that a little bit further, there's a follow-up paper by the same authors. So this is called Hidden Fluid Mechanics. And this one inversely discovers not only the pressure field, but also the velocity field as well. So essentially the assumption is that you only have access to this this sort of scalar field, this CT, and some governing transport equation for that scalar. And yeah, the physics-informed neural network essentially is capable of inversely discovering all the solution fields that are attached to that. So what is a pin? So let's say we want to use a fully connected neural network to predict some function, potentially complex function U, such as this blue curve here. And the only constraint we're using is a sort of measurement loss. So we are minimizing the error between our predictions and the data we have. So to accurately reconstruct this function, we would need a lot of data, which is kind of highlighted by this figure here. I will admit this isn't an actual neural network prediction. This is just a cubic spline, but I think, yeah, the same effect would happen if you did train an actual network on that. So yeah, we need a lot of data essentially if we're using this sort of simple network setup. And this typically isn't really feasible if we're working with real world data, particularly when we're looking at physical systems, because we usually have quite sparse or noisy data. So now imagine we know some kind of a priori knowledge about our system. So for instance, say we know that U is governed by this PDE over on the right hand side with dx of U equals G. We can then encode this existing information into the loss function as a soft constraint. So the way we do that is we reformulate it as a residual, and then when we minimize this this function f. This essentially constrains our predictions to satisfy the PDE. And this facilitates this training in this kind of small data regime. So it doesn't end at governing equations. We can actually include anything in our loss function really that is definable as a residual. So boundary conditions, initial conditions, symmetries, yeah, anything that you can write in an equation and minimize basically. So just to summarize, fully connected neural network plus physics-based loss constraint equals a pin. So simple, basically. So how does this work in practice? So we essentially have two different training passes. So we'll have our data pass, and this might include boundary conditions or data that's sort of dispersed in the domain. Say we have n measurements that form a sort of point cloud XD. We pass these coordinates as input, and we generate predictions at these points and minimize our error between our prediction and the data at that point. Then the second pass, which will be the physics pass, here we, as I said before, we form a residual of our PDE, and we generate a point cloud XP kind of within our domain. And typically, you want your physics point cloud to be far denser than your data point cloud. And this is okay because it's much more expensive to actually acquire data throughout the domain than it is to just, generate random points. So yeah, then we pass these points through the network, and then we generate all the necessary gradients using automatic differentiation. So in TensorFlow, this would be written as tf.gradients, which allows you to calculate the gradient of your output with respect to your input. Then calculate the physics loss. Again, this is usually the mean squared error, and backpropagate our gradients. So I thought now it might be quite nice to go through the original architecture that was used in the first paper, and kind of build on that with sort of key ingredients that have been kind of iteratively improved on in the literature. So the initial architecture works really well for sort of simple problems with simple PDEs and kind of small data sets. But commonly, as I have found, and anyone else who's worked with pins before, I know you, it doesn't really work that well in more complex situations. So where you have real data, for instance, or with more complex PDEs. So the first thing of note is that the loss function in the original paper kind of has equal weighting between the different loss components. So essentially, your data loss and your physics loss is given the same weight in the loss function. So the problem with this is that it doesn't really account for differences in gradient contributions from each of these terms. So one thing you can do to fix this is kind of come up with weights beforehand that stay fixed throughout the training process. For instance, you attach a weight of 100 to the data loss if your data loss isn't being minimized properly. But the issue with this is that it's obviously very problem specific, and you have to tune these weights every time you train a new network. So Wang Catal in 2020, this paper is actually really good. They look at a lot of the common issues that you'd encounter when training physics-informed neural networks. But one of the things they noted was this difference in the backpropagated gradients or the contributions from each term. So these two plots here show the distribution of gradients in the second and third hidden layer. So rad theta LUB is the boundary condition loss and LR is the physics loss. So what you see is that the weights for the boundary loss are sharply centered around 0. So there's a minimal contribution to the training of the network from this loss component. Whereas for the physics loss, you see a flatter distribution, which means that there's more contribution from higher gradients, which means essentially your network learns how to fit to the physics, but not this boundary condition in this term. And I've actually found this with my own work where there's of course a trivial solution where your network will predict everything to be 0 because that automatically satisfies the physics. So if your contribution from your physics loss component is too high, then your network will just predict 0 everywhere. So what they propose is a dynamic weighting scheme. So they introduced this this loss weight lambda I. So lambda Li can be any sort of additional loss component, say data. And they update the weights using this this algorithm here. So lambda hat is the maximum gradient with respect to the physics loss divided by the mean gradient for whichever loss component you're using, loss component I, basically. So this works quite well. I use this in my own work, or a variation of this, but there have been other algorithms that have been proposed, for instance, using trainable loss weights. So secondly, the activation function. So in the original paper, they use a fixed hyperbolic tangent, which is fine again for simple problems. And actually, you know, you will get decent results with more complex problems as well, I've found. But compared to some of the sort of competitors that have come out since, it offers quite slow convergence, and particularly struggles to capture the kind of high frequency solution modes. So this is kind of linked to an issue called spectral bias, which affects not just pins actually, but any sort of feed forward neural network, where your network will tend to predict the smoothest possible solution, kind of the lowest, predicts the low frequency components first, and then after a very long time of training can slowly start to pick out the high frequency components. So I'm going to talk about two alternatives. So the first is these adaptive activation functions that were proposed by JAGTAP. So essentially this just introduces a trainable hyperparameter alpha. So you can take any sort of standard fixed activation function and add in this scaling term alpha, and this is global, so every layer uses the same common alpha value. And this hugely increases the convergence rate of the training process. So we can see this on the left-hand side here. So this is with a fixed activation function. So at 22,000 iterations, so the sort of lime-coloured crosses, you see that even after 22,000 iterations, it struggles to capture these high-frequency modes in the center of the graph. Whereas with the adaptive activation function, even at 8,000, we're starting to capture these solutions. And yeah, by 22,000, the whole solution is fully captured. So JAGTAP was also provided some more solutions here. So there's a kind of locally adaptive version of this. So this is local to each layer, or I think in space as well, different parts of the domain. So this alpha is selected layer-wise rather than a global alpha. And then Rowdy activation functions, which I'll let you Google, is quite spicy.
There was random activation with the alpha, but I don't really use random because it's you always need a activation function that is differentiable.
Yeah, so these these functions weren't exclusively made for physics-informed neural networks. So they have some examples in there. Can't remember some non-physics informed examples, but the paper was mainly focused on pins. I think you can train with a ReLU. I understand the logic behind not being able to, because you have the negative bound, but yeah, anyway, so we can ignore the ReLU for that. So the second activation function, which is the one that I actually use in my work, is the siren activation. So essentially you replace your activation function with a periodic sign, and you have to use this kind of special initialization scheme where you draw from this uniform distribution here. So this again offers improved performance in capturing high frequencies, so kind of dealing with this issue of spectral bias, faster convergence, and also captures the derivatives more accurately, which is shown from this figure here, where you have there's an image, and we see our predictions using ReLU, Tanch, and Siren. And you can see that for the second derivatives of our image, so obviously the ReLU doesn't have a second derivative, so you don't get anything from that. But comparing the Tanch and the Siren, you see that even the small details kind of in the grass down here are still captured well. This has something to do with the fact that the obviously the derivative of a sine is a shifted sine function, so the derivatives kind of have the same form as the original function, I think.
What's the task here? How do they compute the grand truth is?
Yeah,
Is that,
I think it's just trying to reconstruct the image. So essentially the loss function would just be pixel values. I think that's what it is. And then the derivatives. No, I think it's you're passing position as an input, and on a pixel-wise basis, you're minimizing to the pixel value, I think.
This is just a demonstration of the side.
Yeah, sorry. Yeah, this isn't. No. Again, this wasn't developed specifically for pins, but it works well in a saying. Okay, so the next issue is the distribution of the physics points or the collocation points. So in the original paper, these are either randomly distributed in space and time, or uniformly selected using Latin hypercube sampling. I don't think there's too much wrong with this. The only issue is that it can be inefficient if you are using a very high density, particularly in regions where this high density isn't really required. For instance, where you have like low solution gradients. So there's more efficient ways of doing this. So Lulu's paper that came out in 2021, they proposed a scheme called Residualbased adaptive refinement. So essentially what this does is every sort of fixed intervals of however many 50 or 100 training iterations, they evaluate the kind of the physics loss distribution across the domain, and then for regions where you have a really high physics loss, they increase the density of points in those locations. So this example here shows a solution of the Fergus equation, and these little green crosses across the shock region here are points that have been added to the collocation cloud. And then yeah, you can see from these plots at the bottom here that the pin with this scheme switched on approximates the shock much more effectively than when it's switched off. So effectively what this does is that you keep the same density across the whole domain, but it shifts points from regions where they're not required and moves them to regions where you have high physics residuals. So the last one is not really an issue as such. So the original paper uses the LBFGS optimizer, which is a quasi-Newton method. It's actually really accurate, second order, but it's a batch-wise optimizer. So you can only use it on small data sets, essentially, because you can't use MIDI batching. So again, works for small, simple problems, but you run into memory allocation issues if your data set is too large. Typically, Adam is used, as is common kind of across most deep learning fields. The Adam optimizer is, almost exclusively used for this. But I do think some investigation would be worthwhile into kind of generating mini batch versions of these quasi-Newton methods, given their accuracy advantages. So I'm just going to move on to my work now and talk about some of the issues that I've had. So my work is centered around super resolution of 4D flow MRI in left ventricle, and I use pins to do this, obviously. So 4D flow MRI, if you don't know, is a kind of blood flow imaging technique which allows you to construct these time-resolved 3D velocity fields in the cardiovascular system. The only issue is the data is quite low in resolution in both space and time, and suffers from quite strong noise artifacts, particularly in studies in the heart chambers where I'm looking. So
how do they actually measure this?
So you basically measure the phase change in spins of protons. So blood, that's moving, if you fire 2 gradient pulses at it using your MRI machine, the change in spin of these protons is directly proportional to the velocity. So Yeah,
So you get a point-wise estimate of the blood flow.
exactly. Yeah,
But,
yeah.
do you control what points you want to put those?
Yeah. So, so if you see these data coordinates on here, it's usually you have sort of a resolution of like 1.5 millimeters in plane, and then sort of 2 to 3 millimeters plane wise. No, it's okay. So yeah, so these the issue with the low spatial resolution and noise is that these hemodynamic quantities that could be clinically useful, such as vorticity, stresses, the velocity field itself, are inaccurate, obviously. And this is particularly relevant for derived variables. So if you're trying to take a derivative of a noisy velocity field, then yeah, it's almost pointless, really. So yeah, this is the model, the model I use. So I have 3 loss components. So I have the velocity data, the 4D flow MRI, the boundary condition. So I use just the no slip condition on the moving wall on the endocardium. You don't know anything about the inflow and outflow conditions. So yeah, that's the only boundary condition I can apply here. And obviously the governing equations. So the Navier-Stokes equations govern all fluid flow. So that applies to blood as well. And this little animation on the side just shows the distribution of our different points. So our data coordinates are structured on a regular grid throughout the domain. Our wall coordinates are all attached to the wall, and then the physics is just scattered throughout the domain. So, as I said before, I use the loss weighting scheme that I had mentioned previously, or a similar version. So I use one that was actually proposed a year later, which instead just takes the mean of the physics gradient rather than the maximum. So the reasoning behind this is, well, when I originally tried to work on this problem, the physics-informed neural network just predicted zeros everywhere. So it's completely untrainable without these loss weights. And I did start doing it with fixed weights, but of course that's completely problem specific. So every time I moved on to a new case, I'd have to go through this tuning process again. So I would say if you are starting out with a pin of your own, this is the first thing that you should implement, definitely. So the activation function I'm using is the siren. And again, just like I mentioned before, so ventricular flow is transitional and chaotic, and kind of have flow features across a range of length and time scales. So we need to be able to capture the small scale flow features. And the siren sort of allows us to do this. And yeah, so I'm just going to show some quick results. In fact, I might just skip these two so we can get onto the hands-on. You sure? Okay.
I want to see them anyway.
So I've been working mainly on synthetic cases. So the issue with 4D flow MRI is that I'm trying to super resolve something that is already the gold standard. So there's nothing to validate it against. So what I've been doing is generating synthetic data sets using CFD, and then downsampling these using sort of MRI specific technique so that I sort of replicate sort of true 4D flow data. So this case here is a 2D idealized ventricle, so it's a moving boundary problem. And the training data for this was downsampled by a factor of 5 in time. So I take every 5th time point. And this is noise free, this example, and I'm looking at the effect here of the spatial downsampling rate. So here we have the training data. So this is downsampled by a factor of 8 in space, and this is 16. And as we see at both downsampling rates, capture the velocity field pretty well. Definitely better in the lower downsampling rate, and especially compared with the cubic spline, which is kind of sitting there to make me feel better, to be honest. So we see the same with noisy results. The spatial upsampling capabilities are hindered slightly by the addition of noise, but we are using a lot of noise in this data. So this is 15% Gaussian noise, which we had in the case space. And again, we see it's quite effective at denoising as well as upsampling. A good agreement. Oh, and also, just a reminder, I'm not using any pressure data whatsoever. So this pressure field that's derived at the top is constrained only by the physics loss component. And it's just a quick animation of my predictions side by side with the ground truth. So decent qualitative agreement. There's slight sort of flickers of the jet in diastole, but it is quite an extreme downsampling rate time. So I probably wouldn't need to do it this much in with real data. And do I have it? Yeah. So this is a 3D synthetic example. So similar to the 2D case, CFD generated downsampled using a specific downsampling strategy. So here what we're looking at is the iso surfaces of the Q criterion, where the Q criterion equals 100. This essentially picks out regions where you've got highly rotating flow. So we use it. This is what the training data looks like. So this is downsampled by 5 times in time, and this is 10 times in time. And for both of these, you see, yeah, pretty good reconstruction of the coherent structures in the flow. Yeah, that's me. Thank you.
Question time. I have loads of questions, but I'm sure other people have. Do you want to do questions and then we'll introduce the stuff we work on after the topic?
Yeah. Let's do that. Yeah. So any questions?
I have a question. Can I get that?
Great, yeah, go on.
Great, thank you, Fergus. Very informative. Can you say something about other parameter choices like network size, learning rates, and so on?
Yeah, so I have treated these as so I use optimization on a kind of case-wise basis to determine these. So I've done that for 2D studies and 3D studies. The network size is roughly the same. So the depth was, I think, 9 layers for both, and a width sort of between 700 and 800. But yeah, I think that's still, I don't know of any kind of hard rules of how to construct the size of the network at this point. I've found actually that it scales more. So the 2D simulation oddly required a larger network than the 3D. So yeah, adding another dimension doesn't seem to make the training process harder. Yeah.
My first question is about the temporal aspect of this. So in your loss function, do you use more than one time step, or is it like an instantaneous snapshot? It's
So your training examples are points, basically. So attached to this point, you have the position in space and the position in time as well.
right.
So essentially, when you pass the downsample data, all you're doing is passing less data to the network, basically. So instead of evaluating the your data loss term every time step, say you do it every 5 time steps.
Okay, but it's not like the network knows like this is another observation of this spatial location 15 seconds later or something. Like, because you're feeding every observation you've got in the identical way. So,
Yeah.
So
Yeah.
like with you think of like an LSTM, right?
Oh, it's in sort of extrapolation.
Well, there you're feeding samples over time, and you think here's a time series to predict the next thing. They're actually every observation it's given is like this is a observation in space and time.
Yeah.
And I'm not going to tell you that it's related to this other one. I'm going to give you that's just another observation that instant.
Yeah. So I guess that's one of the issues with pins is that they are bad at extrapolation, but they're good at interpolation. At least the formulation that I use. But because I have periodic in time velocity fields, that doesn't work too badly in mine. So I use, well, I didn't actually put it in the slides. I now use a periodic boundary condition as well. Yeah. So
you can imagine the flow at one point, at one time affects the flow at a neighboring point at a different time, like which is similar convolution.
Yeah.
You might tell that this thing is just quite. I think it's really cool that it does so well, not knowing anything about the spatial.
Yeah. I mean, as you can tell from the kind of simplicity of the setup, there's so much scope for kind of increasing the complication or the complexity of the network structure itself. So yeah, for instance, using a convolutional neural network or point net. I don't know much about them, but Ben's working with those. They seem quite good.
overseen it, like, how do you something being too complicated, as we can?
I think that probably plays into the ties in with the spectral bias issue, is that it tends to not hallucinate things that aren't there, if that makes sense. Like if it can fit to the smoothest possible solution, it probably will do that. There are scenarios where it will be too smooth, which is, for instance, why you need to use these more complex activation functions. But yeah, that's my understanding. I mean, yeah, no, I don't know. But you don't need to encode anything extra in there to prevent that there.
You have to apply things like standardization, normalization, and then you have to propagate that into governing equation somehow as well.
That's like a loaded question. Yeah. So I think you can do it without. So what I do is I non-dimensionalize all the equations before I use them in my network, and then I standardize the spatial inputs. But then I also pass the kind of standard deviations that are derived from that into my governing equations. So they don't do that in the original paper. It seems to work fine, but I thought it was more fluent to also include those. But yeah, the non-dimensionalization is actually quite important, because if you have if you're predicting two different variables that vary on very different scales, like pressure and velocity do, you want them both essentially to be sort of centered around zero. So yeah, that's a step you need to do as well. I didn't include that in the slides, probably should have. Any more questions?
So can you just summarize right from the beginning again what the for? I just think I sort of get it now, but I'm still a little bit hazy. So it's a situation where you have some observations.
Yeah.
And you want to fill in a blank in space and time between them, right?
Yeah. So I think the original motivation was kind of using them in scenarios where you have no information inside your solution domain,
Right.
and using only boundary conditions and initial conditions to predict that, which, for example, this does. But because the data doesn't have to be restricted to the boundaries, you can also scatter this in space and time, which is why it fits quite nicely with what I do, where I don't have a complete set of boundary conditions, but I do have these data points which constrain my predictions. As I say, I think it works better as an interpolation tool rather than extrapolation. But yeah.
So let's say you train this one on this heart situation with blood.
Yeah.
What is it then actually learns? So if I went and not put blood, but I put some other fluid in someone's heart, I'm not doing this. You have a fluid. It wouldn't work, right?
Oh, it would work if you made measurements of that other fluid and then
trained it again.
Accounted for that in the in your PDA. Yeah.
Yeah, but is it learning something about the fluid? Like if I put blood through some other structure, would it do good predictions, do you think?
No, it's completely, yes, sorry. This is the big problem with PIMS, is they're completely problem specific. So you have to every time you move into a new domain with a new fluid or any change to the set, you have to retrain it. Interesting. Which kind of makes sense if you look at the structure, because all you're passing as an input is space and time. So all it's learning is, for one specific case, what is the solution?
On that location in space.
Yeah.
Right.
Yeah.
Okay. So it does actually in that way maybe learn at this point next to this other point.
Yeah.
Has a relationship.
Yeah, of course. Yeah.
At least, and then the next step is with operator learning, because operators at the PD, so once putting the operator or people out of this time. Operator learning try to learn all these. So we can all the boundary computation or this, they try to learn the operators, so it's basically recipes, it's more like a solve,
Yeah.
Instance.
Right.
So
Yeah.
Once we get this.
I mean, I think there is a bit of effort in looking into including kind of geometric representations as inputs as well, like learning the structure that you're working in.
Right.
But my thinking is that if you can accelerate the training enough, they're still useful in their own right. Like it's still far faster than running a CFD simulation.
Right. So has anyone, well, I can keep asking questions. I was going to ask one for us and then we call it. But like, if I then gave it a point that was outside of the heart, like
Yeah.
just outside your measurement, has anyone tried to like work out what domain is it comfortable in? You know what I mean? Like, where does it work? Because it must have learned something about blood in this application.
Yeah. It would give you a prediction, but
Right.
that would be garbage, obviously. Yeah, I'm not too sure. Yeah.
Might try that one. I guess.
I mean, there's the inverse aspect of it. So if you didn't know, for instance, like if you wanted to discover the viscosity of your blood,
Yeah.
you would leave that as a trainable parameter, and it should, in theory, be able to tell you what the viscosity is in that domain.
How many people in this school using pins? Or raising hands?
Right, hands up.
So,
So we know we can ask you questions as well. Oh, wow, that's a lot of people. Also in health or other applications? Same group. You're more